Ladies and gentlemen, now, we will start the second and last lecture of the case study module. We will start analyze cause and effects using the measured and collected data, create multivariable analysis, determine variance components, and assess correlation. The collected data in the previous phase will be checked for linearity before further steps. We will make data transformation if only needed. We will check the data collected from the machine interface and clear our control units. These data are cuts per 100 kilometers, winding process speed, weak places per 100 kilometers, yarn breaks per 100 kilometers. We will perform for the number of cuts per 100 kilometers data the normality check using Sigma Excel. As it is clear from the plot, data distribution of the number of cuts per 100 kilometers is normal. Then we will perform for the winding process speed data the normality check. Also, the winding process speed data distribution is normal. However, for the number of weak places per 100 kilometers data normality check, we found that the data distribution of the number of weak places per 100 kilometers is not normal, and data transformation should be done. The data transformation has been done using Box-Cox power transformation with lambda equal to 0.31. The number of weak places per 100 kilometers data, after transforming, has been checked for normality. And the data distribution is now normal. Number of weak places per 100 kilometers data after transformation has been checked for process capability. Process is capable, but not centered. Please note that before transformation, the process was not capable and not centered. Now, we will perform number of yarn breaks per 100 kilometers, data normality check. From Anderson-Darling normality test, A squared is equal to 3.445, and p-value is equal to 0.00001. So, data distribution of the number of yarn breaks per 100 kilometers is not normal, and data transformation should be done. The data transformation has been done using Box-Cox power transformation with lambda equal to 5. Number of yarn breaks per 100 kilometers data after transforming have been checked for normality. Transformed data distribution of the number of yarn breaks per 100 kilometers is almost normal now. Number of yarn breaks per 100 kilometers data after transformation has been checked for process capability. Process is capable and almost centered. Please note that, before transformation, the process was capable, but not centered. In order to ensure that a balanced list of ideas have been generated during brainstorming, or major possible causes are not overlooked, and to explore all the potential or real causes, root causes or inputs that result in each single effect or output in our project, we will study the root cause for two main problems. Please pause the lecture and check the cause and effect diagram of the low-quality problem due to high number of remaining faults in the produced cones. Also, please pause the lecture and check the cause and effect diagram of the low production efficiency problem due to high WIP. We will utilize these diagrams to answer the questions in the next section of 5 whys and proceed to the improve phase. 5 whys analysis is a problem-solving technique that allows us, in addition with a cause and effect diagram, to get at the root cause of a problem fairly quickly. We will analyze our two main problems in our project in details with a 5 whys analysis. For the cause of high number of remaining faults in produced cones. Why there is high number of remaining faults in produced cones? Because there is high variation in the number of cut faults, and also in the number of thin places, and the number of yarn breaks. Why there is high variation in the number of cut faults, the number of thin places, and the number of yarn breaks? Because the clearing limits are not adjusted well, and the quality of bobbins from spinning process is not under control, and there is a lot of fiber accumulation on the spinning machine. Why the clearing limits is not adjusted well, and the quality of bobbins from spinning process is not under control, and there is a lot of fiber accumulation on the machine. Because the operator does not clean the machine well, and does not adjust the clearing limits as the manual, and the maintenance of spinning machine is not done according to the given table for machine manufacture. Why the operator does not clean the machine well, and does not adjust the clearing limits as the manual, and the maintenance of spinning machine is not done according to the given table for machine manufacture. Because the operator and maintenance team have not trained well on the machine operation and maintenance. Why the operator and maintenance team have not trained well on the machine operation and maintenance? Because the management does not apply the total quality management and does not involve the operators and maintenance in quality issues. For the cause of high number of whip before winding process. Why there is high number of whip before winding process? Because there is high variation in the machine speed, and the setup time is high, and also there is variation in number of cut faults. Why there is high variation in the machine speed, and the setup time is high, and there is variation in number of cut faults? Because the machine speed and clearance limits are not adjusted well, the setup time is done during the stoppage of machine, and the spindle's stop time is high without reason. Why the machine speed and clearance limits are not adjusted well, the setup time is done during the stoppage of machine, the spindle stop time is high without reason. Because the operator does not adjust the machine well, and does not adjust the clearing limits as the manual, and leaves the stoppage spindles without start them, and also the maintenance of spinning machine has not been done according to the given table for machine manufacture. Why the operator does not adjust the machine well, and does not adjust the clearing limits as the manual, and leaves the stoppage spindles without start them, and also the maintenance of spinning machine has not been done according to the given table for machine manufacture. Because the operator and maintenance team have not trained well on the machine operation and maintenance. Why the operator and maintenance team have not trained well on the machine operation and maintenance? Because the management does not apply the total quality management and Lean Six Sigma and does not involve the operators and maintenance in quality issues. In order to emphasize the cause of the lower production efficiency, we use the Pearson correlation coefficient, designated as R, which reflects the strength and the direction of the relationship between two variables. A high correlation between the actual efficiency, which reflect on the whip number, and the stop time, which represent the stoppage due to operator problem or setup time of the machine. The regression calculation outputs are R power 2 is equal to 0.934, and adjusted R power 2 is equal to 0.933. In order to analyze the collected data for the 3 shifts, 7 days, using a special software called Quantum Display Unit, and track the order in which the data were generated by the process. Part of these data is summarized in the table, and use them to generate a several time series plots, or run charts. We mark off the data units on the vertical y-axis and mark the sequence, plot the data points on the charts, weak places per 100 kilometers, process speed and yarn faults per 100 kilometers, and draw a line connecting them in sequence. Then determine the median, and draw a line at that value on the chart. The weak places shows that the number of points, which are not in the median, are 19, and number of runs are 11. The yarn faults analysis shows that the number of points, which are not in the median, are 19, while the number of runs are 11. The speed analysis shows that the number of points, which are not in the median, are 19, and number of runs are 12. Common causes of variation in our project: inappropriate procedures in machine adjustment and setup, poor maintenance of machines, and clearers, poor working conditions, dirt, temperature, quality control error either in fault elimination or tension adjustment, ambient temperature and humidity. While special causes of variation in our project: poor adjustment of equipment, machine speed, clearers setting, splice setting. Operator has not been trained according to the standard levels. Faulty controllers. Operator absent. Now, we will start to improve and evaluate solutions, implement variation reduction, standardize process and assess risk factors. The following are our process lean metrics: cycle time and throughput rate, interval of time between two successive outputs coming out of a workstation or process. Every winding position produce one cone in around 3 hours with capacity of 2 output lots per shift. And the throughput rate of the machine is 2 lots per shift. Bottleneck. The winding process is the bottleneck of the mill, and by improving the quality and production rate of it, the whole mill production rate will be improved. Lead time is equal to cycle time plus waiting time. Cycle time is about from 3.5 to 4 hours, while waiting time is between 30 minutes and 1 hour, stoppage time and setup time. Process utilization is equal to cycle time divided by lead time, which is equal to 75%. The actual utilization from the collected data is 72.65%. Setup reduction is the process of reducing changeover time. Since setup activities add no form, or fit, or function to the product, they are by definition non-value adding. The benefits are included reducing lead time, which resulting in improved delivery. There are two types of setup. Internal setup is an activity that must be performed by the process operator during machine stoppage. The operator was adjusting the clearer's limit and the machine settings, speed, tension, package size, during machine stoppage, and this adjustment taking from 30 to 60 minutes. External setup is an activity that could be performed while the equipment is producing parts, or the process operator is conducting other value-add work. To reduce setup time, the following procedures have been done. Good training for the operators and maintenance team from the machine manufacturer. The management changed the setup procedures to do all the necessary settings for machine and clearers during the running of machine and save them in database. Then the operator stops the machine for only 5 minutes to recall these settings before start the new lot. Additional action: the production and quality manager start to use a synchronization adjustment, which is a new feature in the yarn clearers central unit for the yarn clearers for the new lots and material types to reduce the setup time. Total production maintenance, TPM, is a system of maintaining and improving the integrity of production and quality systems through the machines, equipment, processes, and employees that add business value to the organization. The main problem in the mill of our case study is the separation of production and quality and lack of training of the operator. Therefore, as TPM, the operators have been trained to adjust the machine to maintain the high quality and high productivity at the same time. In addition, the required maintenance has been done in cooperation between maintenance department and production department. The operators and maintenance staff have been involved in the quality and production. TPM focuses on keeping all equipment top working condition to avoid breakdowns and delays in manufacturing processes. Improve phase number 1. Return equipment to reliable condition through clean machine thoroughly and perform repairs. Improve phase number 2. Eliminate breakdowns through eliminate factors contributing to failure, such as clean the tensioner and splicer before entering the fibers inside nozzles, adjust the belts well, supply only cleaned and dry air to the machine, and lubricate the moving parts according to machine manufacturer's instruction. In addition, we try to improve accessibility to the part or area so you can regularly clean, lubricate, adjust, inspect. Improve phase number 3. Develop TPM database by forming the necessary document for all preventive and predictive maintenance procedures. Improve phase number 4. Eliminate defects through install visual controls, help prevent future failures by training maintenance staff in proper techniques to implement 5S housekeeping and organization, regularly review and improve machine performance by perfect adjust for machine speed and splicer and tensioner, and readjust the yarn clearers and clearing limits probably. Visual controls include a variety of displays and visual markers in the workplace, which includes the safety indicators and checkboards. 3 checkboards have been designed and used. The first checkboard used to monitor production and stop time for each machine in each shift. The second checkboard used to monitor adjustment for each machine in each shift. The third checkboard used as personal training board. As a result of the previously improvement tools, a remarkable reduction in the weak places, clearer cuts and their variations has been achieved, which improve the quality of produced yarn. Implementing 5S. Visually organize the workplace. Clean up fibers on floor. Clean up the machine and winding position. Make cleaning checklist card and attach it to each machine to be filled during each shift. Remove excess supplies from area. Sweep floor. Place tools on board. Set periodic inspection for clearance and ordering. Documents process steps and other operating instructions. Documents all job aids, user guides, reference materials, troubleshooting guides. The purpose of this step is to design a structured approach in order to identify the ways in which a product, service, or process can fail, estimate risk associated with specific failure causes, prioritize the actions to reduce risk of failure, and evaluate design validation plan, product or service, or current control plan, process. Prior to developing the FMEA, a team should be selected and a process map developed for the process in question. Complete FMEA for winding machine with high variation in the cuts per 100 km is shown in the table. The higher potential failure affects is the remaining faults in the produced cones, due to causes of wrong adjustment of yarn clearers. In order to control the process, we need to check clearers control unit process controls. It has the higher RPN with 175. The second potential failure affects is the remaining faults in the produced cones, due to supplied bobbins have too many faults. And to control the process, we need to check samples from produced bobbins. It has the second higher RPN with 126. Complete FMEA for winding machine with high whip, before winding, is shown in the table. The higher potential failure affects is the high whip before winding, due to causes of the machine setting is wrong. And to control the process, we need to check winding machine settings. It has the higher RPN with 150. Complete FMEA for wrong package density produced by winding machine is shown in the table. The higher potential failure affects is that the package density is wrong, due to supplied bobbins are wrong. And to control the process, we need to check samples from produced bobbins. It has the higher RPN with 189. Now, we will start to control the process and implement control charts for key variables. Also, we will implement mistake-proof processes and evaluate results. The control charts is used for establishing a measurement baseline, detecting special cause variation, ensuring process stability, and enabling predictability, monitoring process over time, and confirming the impact of process improvement activities. The data of cuts per 100 kilometers prior to the improve phase have been collected as individual measurement in sequence per shift and arranged in table. The average control charts of XMR of the number of cuts per 100 kilometers. All points are locating inside the limits, which indicate that the process now is under control and no special cause of variation. The range control charts of XMR of the number of cuts per 100 kilometers. All points are locating inside the limits, which indicate that the process now is under control and no special cause of variation. The data of winding speed have been collected as individual measurement in sequence per shift and arranged in table. The average control charts of XMR of the winding speed, with all points, are within the limits, which indicate that the process now is under control and no special cause of variation. Also, the range control charts of XMR of the winding speed, with all points, are within the limits, which indicate that the process now is under control and no special cause of variation. The data of weak places per 100 kilometers have been collected as individual measurement in sequence per shift and arranged in table. The control charts of XMR of the weak places per 100 kilometer, with 2 out of 3 successive values in Zone A and 4 out of 5 successive values in Zones A and B. The process is totally lack of control in the number of weak places, and there is a special cause of variation in the weak places, and further improve over the time must be done. By implementing the Lean Six Sigma different techniques, a significant change and effect have been done, and noticed either in the quality level of the produced cones, and satisfaction of the weaving miller in the production of the whole spinning mill, and the flow of the work process. In addition, a notice saving in the quality and production costs has been achieved by implementing the Lean Six Sigma, by reducing the waste and non-value added times, and the low-quality refused cones from the weaving process. More control on the process over time should be done to maintain the achieved quality and production level. Training of the operators and maintenance staff should be continue in regular basis, involving both production and maintenance department in the quality control, will help to keep the improvement of the process and keep the clean organized workplace with correct climate conditions. A remarkable notice has been recorded during the research that there is a big interference between the 5 DMAIC steps of LSS. Analysis for the process has been done during the measure process, additional measurements and advantage analysis have been done during and after improve process. In addition, improve and control processes are very interfering. This is the end of the second lecture of the case study. Thank you.